Hi everybody, it's Kyle. It's nice to see everybody again. I know it's been a while since I made a video, but I am back and I'm going to be solving the following problem, which is finding the electric field at distance d above the center of a circular loop that carries a uniform line charge lambda. And we're going to assume that the loop is in the xy plane. Okay, so I've sort of drawn the picture here already. And the black circle is the loop and the blue is sort of the coordinate system that I've drawn. But essentially, what we're going to do is that we're going to start from first principles. I'm going to use the electric field formula that's given in Griffiths if you have a uniform line charge. So if you remember from Griffiths, this equation starts off looking something like 1 over 4 pi epsilon naught r hat over r squared times dq. But remember, dq is this infinitesimal amount of charge, and we say that dq is equal to, for a line charge, is equal to the uniform line charge density lambda times dl, right? Which is why I have it written as lambda dl right there, okay? So that's sort of where I start from, and the main task is that we're going to identify what exactly this r hat vector is, or script r hat. So I should say that this letter is script r. Okay, so this is script r hat, and then this is just the magnitude of script r squared. And we also need to know what this dl prime line element is. Okay, so first things first, I'm going to find what the script r vector is. And in Griffiths' book, the definition of a script r vector is just this regular r vector minus r prime. Now the the first r, the non-primed r, this is the field point. This is the point where we want to measure the electric field. In this case, it is at the point P. Okay? So at the point P right there, we need to find a vector that describes where that point P is in space. Now that's easy. The P point is at the origin in the xy plane, but it's also a height d in the z direction. So in that case, the vector would be 0, 0, d. Or maybe another way of writing that is just equal to d in the z hat direction, right? So there's zero y and x component length, okay? Now what is this r prime, right? This is the source point. So the source point is pretty much anywhere a source charge dq is located. And that pretty much means anywhere on this ring. So here, let's just call this point, let's call it r, I guess. And we want to find a vector that describes pretty much any general point r on this loop. And the easy way to do that is to go into polar coordinates, right? Because in polar coordinates, at least in Griffiths' book, it's defined as x is equal to s times cosine of phi, where s is just the length from the origin. But in this case, s, remember, is just r, right? So here's r right here. It's just the radius of that loop. So the source charge is located on this wire, or this loop. It's called a loop. I'm not going to say it's a wire, but it's a loop. And all the charge is just located on the perimeter of this loop. And so the x position is given by s cosine phi, or r cosine phi in this case, and the y coordinate is given by s times sine phi, or r times sine phi in this case. Right. So in this case, right, so let's just say this is r and this is equal to r. So those are the x and y coordinates of the source of the source dq, okay? But what is the z component? Well, it's in the xy plane, so it has to be 0, right? So it has absolutely no length in the z direction. So the r prime vector, right? So we're going to write down the x component. This is r times cosine phi. The y component is r times sine phi. And the z component is 0, which this is just equal to r cosine phi x hat plus r sine phi y hat plus 0 z hat, right? And if we do r subtract r prime, this should just equal, right? We should just get negative r cosine phi x hat minus r sine phi y hat, and then we'll have a plus d z hat. Okay, looks good. And remember, this is the script R vector. Now what I'm going to do is I'm going to find what exactly is the magnitude, or the magnitude squared, of script R. The way we can do that, remember, is we can just take the square of the sum of the components, remember? So the magnitude of a vector, right, so the magnitude is just equal to the square root of all the different components, right, which in this case is just r cosine phi quantity squared, or actually it's a negative there, plus a negative r sine phi quantity squared, plus a d squared. Now, I'm not going to show this, but this will simplify too because of the cosines and the sines there, right? You're going to have an r squared, and then you'll have a cosine squared plus an r squared sine squared, so that should just give you an r squared. So this should give you the square root of r squared plus d squared, okay? And we want the square of that, right? We want magnitude squared, which is just equal to r squared plus d squared. Okay, so with that in mind, we have, I think, two of, oh, actually, sorry, we haven't even had the main piece, is the script r hat vector, which of course is just script r vector over the magnitude, which, okay, since we know what the magnitude is now, we have, let's just see here, we'll have negative r cosine phi x hat minus r sine phi y hat plus dz hat, and then we have the square root of r squared plus d squared. So what I've just done now is I've taken the script r vector and I've divided it by its magnitude to give us the unit script r vector. Because remember, if you look in the formula here for the electric field, we need both the square of the magnitude in the denominator, and we need the script r hat vector. Okay, and we're almost there. So now that we have those two things, what is this dl prime vector, right? Well, the dl prime vector, which is the thing we have to integrate over to get the electric field, it's not that bad, actually. This is just sort of the path that the charge lies on, or the infinitesimal length on the path that the charge lies on. But the path is essentially this circle, right? This circular loop in the xy plane. So I'm going to go to red here, and we can think of this as being a dl prime right here. This is sort of the path that you have to integrate over, or where the charge lives on, right? And if we remember just basic, I guess, trigonometry and circles, we know that the arc of this circle is given by the infinitesimal change in the angle and the radius, or otherwise we can just write that as r times d phi, right? So if we just want to go, we want to sweep out this entire circle, the path length is given by r d phi, okay? Or that's just the arc length, right? So this is arc length. Okay, so we have everything now. We have the dl prime, we have the script r hat vector, and we have the magnitude. So let's just rewrite the equation down below. I'm going to rewrite what the dl prime is. So that's just r d phi. Sorry, I know I wrote a big R up there for some reason, but it's supposed to be a little r. Okay, so I'm going to rewrite the electric field formula one more time, just so I don't forget anything. So I have lambda 4 pi epsilon naught. Now I have integral r hat over r squared dl prime, which is equal to, one more time, the coefficients out front. Now r hat is this thing. It's negative r cosine phi x hat minus r sine phi y hat plus dz hat. This is over the square root of r squared plus d squared. Now, what is this r squared magnitude term? Well, that was just r squared plus d squared, right? So we have another r squared plus d squared right there. But we can combine it with the first one to the left of it, right? So if we add these two powers together, this has a power 1, and the square root is a power 1/2. So this should give us an r squared plus d squared to the 3/2. Okay, and last but not least, I need to get the dl prime in there, right? So the dl prime is times all this times r d phi, and we want to know where to integrate over. But since this is a circle in the xy plane, we just have to go from phi is equal to 0, from phi to phi is equal to 2 pi, right? We just got to make a one rotation. So we're going to go from 0 to 2 pi on the angle, and that is the integral we have to do. Now this looks kind of bad, but notice we want to integrate over phi only, so none of the r's or the d's are really going to make a difference here. We effectively have 3 integrals that we have to do, right? Because there's 3 terms in the numerator. But the thing is that integral 1 and 2 both equal 0. And why is that? Well, for example, let's just take a look at integral 1, for example. So integral 1 would be lambda 4 pi epsilon 0, 0 to 2 pi. We have negative r cosine phi, and there's an x hat here, sorry, over the square root of r squared plus d squared to the 3/2 times r d phi. This is an integral in phi only, right? So everything that's not a phi gets pulled outside. So this, so this still stays outside, but also comes out the negative r squared plus d squared to the 3/2. And we also have, let's see, 0 to 2 pi cosine phi d phi. Okay, so this integral right here, right, this just ends up becoming a sine because cosine's integral is sine from 0 to 2 pi. And that just gives us 0 because sine has the same value at 0 and at 2 pi. Okay, so that's 0. If you do it with the second term, that's also 0. So we don't have to worry about those terms. The only term that we have to worry about is that third term. So the electric field looks like now it's just going to be in the z direction, which sort of made sense. We could have just used symmetry arguments from the beginning, but I like just showing this sort of first principle approach where if you have really no idea what to do, you can always just sort of start from first principles, and then the math and the physics will just illuminate the way from there, from that point forward. And so the integral that we want to do is lambda over 4 pi epsilon naught. I keep going up here. We have 0 to 2 pi. We have d times r d phi over r squared plus d squared to the 3/2. And this is in the z direction. I want to make sure I didn't leave anything out. That looks good to me. So again, we only going to be integrating in phi. And in this case, there is nothing that depends on phi. Everything is just pretty much constant in this integral. So we can pull everything out, right? Pull everything out. Let's pull everything out right now. D times r. Now I'm going to write it as r times d just so it doesn't get confused with the differential dr. This is in the z hat direction, and we go from 0 to 2 pi of just d phi, which, this is simple, this is just 2 pi, right? And so now the electric field can now be simply given as 2 pi lambda times r times d z hat over 4 pi epsilon naught r squared plus d squared to the 3/2. And we can simplify this a bit. I will do that. I'll cancel out these pi's, cancel out a 2 right there. So we'll have lambda rd z hat 2 epsilon naught r squared plus d squared to the 3/2. And that is our electric field that we're looking for. So I hope you enjoyed this video. I hope you learned a little bit and this was helpful if you were doing this problem. Please leave a comment and a like. Just tell me if you liked the video and if you think I should be doing more of these in the future. And I'll see you next time. So thanks for watching.